Today we're going to be talking about airflow. We're going to actually run the system. We're going to go through, set up a profile, and then actually make some changes to the system, block off the, kind of simulate a dirty filter, simulate a poor duct system, and then actually show what it does. But before we do that, I just kind of want to talk through it a little bit and talk through some more of the theory, what goes on in the system. We talk a lot about the same things over and over and over again, but the goal is to get you to a place where you both know what to do, but you also know why you're doing it. That's always the goal. So let's start with really practical. I always like to start with the actual practices that you do. When you go up to a piece of equipment, and let's say it's a no cooling call. We'll use a no cooling call as an example. What are some things that are airflow related that you should check every time, regardless of what the problem is?
The filter.
First is the filter. What else? Blower wheel. What are you checking on the blower wheel?
Any buildup on the actual blowers itself.
Any buildup on the wheel. Yep, that's good. What else?
Coil. Evaporator coil.
Evaporator coil. What specifically on the evaporator coil, though?
The underside.
The underside, the inlet side of the evaporator coil is what you need to be checking. So just because you were in there with the blower and you looked down and you didn't see anything. What else? Try to be a little bit more, because those are things that you definitely go in with intentionality to check. I'm going to check the evaporator coil. I'm going to take my mirror and look on the underside. I'm going to check my blower wheel. I'm going to check my filter. Those are intentional. But there are some other things that a good technician will always look for. It may even just be subconscious.
I look in the return grill every time I pass.
Look in the return grill every time you pass. Exactly. What are you looking for when you look in a return grill every time you pass?
See how dirty it is, or if there's another filter behind that.
If there's another filter behind that. Aaron says if it's collapsed, coming apart. Those are all really good.
Sound of the motor.
The sound of the motor. That's a really good one. So what are you looking for with the sound of the motor? I like this. What are you looking for? Abnormal sound. So what are some things that can cause abnormal sounds with the blower motor?
Low, loose.
Static pressure. So what static pressure? High, low? Too high of static pressure. So too high of static pressure will cause what to happen specifically? Eric?
Depends on the type of motor.
Depends on the type of motor. That's the right answer. That's what I was looking for. That's why I picked that, Eric, because I didn't want to have to yell at anybody. You probably would have said Freon.
I passed it.
You probably would have said, yeah, so it depends on the type of motor. So let's say that we have an old school PSC motor and you hear it making a noise. What would an experienced technician think? I'm just gonna wait. Here. Standing here. I'm not in a hurry.
That is overamping.
That it's overamping. Okay, possible, but that's a symptom, not a cause. Wired incorrectly? Probably not as far as noise. Probably not on a PSC.
Well, I'm not thinking there's high static.
You're not thinking there's high static, right? Because high static on a PSC motor, the permanent split capacitor motor, does what to system airflow?
Dramatically lower system airflow.
Dramatically lower system airflow. And the motor does what in response to that?
It does not speed up.
It does nothing. It does nothing. It's like a husband on the weekends. It does nothing.
True.
So all it does is reduce its output. It does not ramp up, and so it doesn't try to compensate. There's no compensation taking place, so it won't be noisier because of high static pressure. A PSC will not be noisier because of high static pressure because it's not attempting to ramp up. But if it is noisy, what are some things that could cause a PSC to be noisy and do cause a PSC to be noisy?
Not the capacitor.
Not the capacitor, right? Well, the capacitor doesn't. It's a fine thing to check, but this is good because what you don't want, and this is something that a lot of newer techs do, every time there's a problem, every possibility is open. So you just check every possible thing that it could ever be, right? And that's okay to some degree, but what's better is to be able to narrow down and find the problem. So if you have a PSC motor that's making a noise, could be the bearings on the motor, could be the blower wheel. In fact, often it is the blower wheel. And what often happens on a blower wheel that makes it noisy? Eli? It breaks. Yes,
The hub
it
gets,
breaks.
The hub gets loose.
The hub gets loose. Yes, and so what will happen is that either the entire larger hub where it attaches to the blades disconnects, or the internal hub where the shaft attaches to that larger inner hub intersection gets loose. And so when that happens, you'll often get a really loud noise. Sometimes, though, that noise will be intermittent. So sometimes it'll squeal really loud and then it'll stop, and it's just a matter of if it finally caught for a second. But it can be an awful, awful noise. So again, I like having these conversations where we kind of go off on little rabbit trails, because there may be things that you pick up on that you haven't thought of before, diagnostically. The topic is airflow, though. All right, so with an ECM motor, if you hear it doing what Matthew was describing, where you hear a lot of air sucking in the cabinet or it's making a loud whining noise or whatever, then you suspect static pressure. You suspect that your static pressure is high. And why does that motor do that when the static pressure is high? Why does the air get noisy and the motor start to maybe vibrate a little bit more, make more noise? Why is that?
Because we're just trying to maintain the airflow it's programmed to be at.
It's attempting to maintain airflow or torque, depending on the motor type. X13 motors, which is a brand name, constant torque motors are going to attempt to maintain torque. ECM or true variable are going to try to maintain airflow. So that's what you watch for. When you hear an air handler that's howling or a furnace that's howling, always stop and look at static pressure. First, before you even check static pressure, though, what are you going to look for? Restrictions, right? You're going to look for the things we just mentioned. Starting with air filter, obviously, then going to evaporator coil. You're also going to look at the blower wheel, but blower wheel loading doesn't make the motor function in the same way as other airflow restrictions. It's kind of we won't get into that right now, but it's not going to necessarily cause that problem. But then you look at things like Bert said, you look at the returns. What are some other things? What are some customer-caused things in addition to air filters that can cause low system airflow?
Closed supply vents.
Closed and supply vents. Why do they do that? Why
Because they're cold in the room.
Because they're cold in the room.
Force more air.
Trying to force more air into another room. Exactly. Did I ever tell you how we used to do air balancing back in my prior company that will not be named? Did I ever tell you that? Well, no, that's how you would check. So the way you check for airflow, especially after you started up a zone damper system, and I still stand behind this. I have no shame in this whatsoever. You take a surveying flag, and those are all over the place. You can pull them out from anywhere. Nobody ever cares. It's amazing. You take a surveying flag. Yeah, it's like, hey, look at these. It's a gift. These are amazing. You take a surveying flag, you bend a 90 in it, and you cut it into little ribbons, and then you tape it onto a piece of PVC. See how fast the blowy blows, and that tells you whether you got good airflow. So when I say stand behind it, I do not stand behind that as an airflow measurement tool, really, but as a qualitative, is a damper open or not? It's actually a great way of doing it. We used to work in these big custom homes in Isleworth and Windermere and all this, and you start up a zone damper system, or maybe two in a house, and you got to go through and make sure each damper opens and closes, and that's an excellent tool for that. And I will not be shamed. I will not. If you comment on YouTube telling me I should be ashamed, it's not going to work, so don't do it, because I won't be. It's not going to work. It'll be ineffective, you know? If you diagnose this machine and you think that trying to shame me about this is going to work, it's not going to. You know, you're going to have to put another TXV in because it's not going to work. Oh, the emotion. Sorry, I'm patting my mic now. That's going to be noisy for the editor. Okay, so what was I talking about?
You were talking about your flag.
Stealing survey flags.
Customers.
Survey flags. Oh, yes. Okay, restriction. So another thing we would do is if we wanted to force more air, so if we had an area that was getting too much air and we wanted to force it to a master bedroom or something else, we would take a piece of duct board, we would cut it a little larger than the internal diameter of the flex. We would then cut it in half so it was kind of flexible, and we could fold it over, and then we'd cut a smaller hole on the inside. Now, the trick was knowing how big to cut that smaller hole on the inside. And you know what science we used in order to figure that out?
Trial error.
Handometer.
Good old handometer, trial and error, yep. So you'd be like, hey, this laundry room, it seems like it's putting out a lot too much air. So I'm going to make the hole in the inside real small. And then you take the grill down, you'd bend it and you'd force it way up in the duct. You know why you forced it way up in the duct?
The inspector don't see it.
No, that might have been a reason. No, the reason is because if you put it right down by the vent, it would make a lot of noise because it would come through. It would be high velocity. It would hit just a portion of the grill, and it would make a lot of noise. So you shove it way up in there so it had a time to become more laminar and fill the duct before it would come out. And so obviously that will cause low system airflow. It's not that it's ineffective at balancing, because you can actually improve air balancing in a house doing that. But along the way, what are you doing to your supply static pressure?
Raising it.
You're raising it, right? It's just like crimping the end of a hose. If you pinch the end of the hose, you're building up more pressure and more static pressure in the hose itself. So rather than that energy going towards flow, it's backing up and it's building up pressure that's forcing against the blower, and it's reducing the amount of air that can go into the space. What are some other things that customers do that we want to watch for?
Move furniture in front of the return.
Yes, they move furniture in front of the return. And it's especially awkward if it's a ceiling return. It's like, man, would you get that couch off the ceiling? I don't know what you're doing in here, but get that off the ceiling. No, so usually it's a low wall direct return, and somebody shoves the couch up against it, right? Or a lot of times people with pets, with a lot, very shitty pets, that can even plug up if they have returns that are kind of, tight. Maybe they're the stamped returns. The actual opening will get plugged. In commercial, you'll see it a lot with perforated returns. We call them perfs. That's what we call them in the trade. We call them perfs. Hey, what you got up there?
I got a
What do you say? What do you say? What do you say?
Purrs.
You got to. No, that's not what we say. That's a whole different thing. That's a whole different problem that we have. No, so because the openings are so small, they get plugged up with dust, and that can actually greatly impact system performance.
Another thing to watch out for with perf grills is they glue a piece of like cardboard, or they put a piece of metal in the center, and the back is fiberglass, and it's usually not supported well. So over time, it starts to sag down onto that piece that now obstructs the end of your duct. So you'll have a whole space that was cool and fine, and then you have to actually remove all those pieces of metal or cardboard to get it to cool again, because it'll kill all your airflow.
Yep. Yeah, perf returns aren't great. They're not the best. What is something else that can happen to the system that you want to watch for that can result in poor system airflow? Double filter, that's good. We talked about that. If somebody, but yeah, you're right. Somebody could put one in a 4-inch media cabinet and then also put a filter in the system.
Cable guys.
What?
Cable guys.
Watch out for cable guys crushing the ducts.
Or
Yep.
pulling them off.
You see all these dead ducks in the attic. And it's
Yeah.
those cable guys. They're just always up there stomping ducks.
Or pulling off the supplies to cool themselves off in the attic.
Yep.
See that a lot. See.
I haven't seen that a lot, but I have heard tell of it. Yes.
You the one doing that?
Yeah.
Not on camera.
What were you-
Collapse returns and supplies.
Collapse returns and supplies, that can happen. The internal liner, especially if somebody made a duct splice and spliced it the wrong direction. So that way the internal liner starts to collapse in. That can happen. You see that a lot on trailers. Real common. Basically you see everything on trailers. All the things you don't want to see.
You look up,
You know,
see things you don't want to
everything-
see.
It's like, oh, what is this, a trailer? I'm going to see something I don't want to see, I felt like I should just keep milking that joke because I liked it, but then I didn't have anywhere else to take it.
There's a lot of things.
It really is. It really is. Bird almost ran into a pony one time. That's
We
good.
also have
That's good.
insulation in the unit sucking into the blower.
Yes, I was waiting for that one. Insulation in the unit that sucks up against the blower. Yep, that's another really big one. So actually, every time you take the panel off of a system, and by the way, it's actually pretty dangerous to take the panel off of a running air handler. Like, when I say dangerous, it's probably not going to kill you, but I've seen people pull panels off, the insulation sucks off, and then it goes and starts shorting out or gets into the blower or whatever. That can definitely happen. Now, the more experience you get, the more you kind of make sure you get a corner and you kind of work it off, but you really shouldn't be pulling panels off while the unit is running around the blower. And I know you're all rolling your eyes at me right now. The entire internet is rolling their eyes at me right now, but I'm just saying.
That's so true, Brian.
And so true. So true.
I'll never do that again.
Yeah. What are some other things that cause low system airflow?
Poor design.
Poor design of what?
Everything.
System?
The whole entire thing.
The house.
Like the mixing boxes.
Whole world.
Yeah.
Okay. All right. Poor design can definitely cause poor system airflow.
Exactly.
We're talking about like after the fact though, right? like after the installation. You're on a service call.
Yeah, but it could be poor design, sure.
Okay.
What's another one? Why do sometimes you have really bad system airflow right after you had a backed up drain?
Water in the return blocking
Water
it.
in the supply.
Water in the return, yep. Either way, if it's downflow, it could be water in the supply, but you will sometimes, especially in cases where you have a flex return, those flexi ducts, they'll hold a lot of water.
Seen that
Yes,
before.
sir.
Oh yeah.
What'd you say?
Especially
gas
with trailers.
Flex return,
Especially the
because that
trailers,
back
once
up
again,
and just holds a bunch
Those
of water.
trailers. They'll fill up with water and that will block either the return or supply. In the case of downflow, it could block the supply. Either way, it doesn't matter. If there's low airflow over that evaporator coil, it's going to result in problems, right? What else? Frozen evaporator coil. Yeah, I mean, that definitely is going to cause low system airflow. Now, often it's low system airflow that caused the coil to freeze up in the first place, but it could be something else. Could be bad TXV.
You forget to cut the return?
Huh?
Forget to cut the return?
Yep, you set an air handler on a platform and you don't cut a hole in it.
I knew
That will definitely. No, let's not be ridiculous. Let's talk about stuff that's actually going to happen in real life. I mean,
Of course,
They
that's
have like
gonna
zone
come on.
dampers.
There's some things that just aren't going to happen.
Forget to plug the fan back in.
Ooh, ooh.
Forget to plug the fan back in.
Chadwick has it.
Failed.
Chad, what?
Say it. Say it.
Failed
Say it.
Failed
What?
zone dampers.
Failed zone dampers. Yep. Yep, definitely. Go ahead, Chad.
That's
What else he's gonna say?
That's what I was going to say.
Oh, failed zoning dampers. Yep, definitely. If zone dampers are failed closed, that can cause it. Now, there aren't nearly as many zone dampers nowadays that fail closed because they're usually spring open power closed. So usually they're just going to blow all the time.
Fire or smoke dampers.
Fire dampers, that's a really good one. Yep. In commercial applications, where at one point in time everything was fine, and next thing you know, like an entire area of a building no longer has air. Definitely look for fire dampers that are slammed shut. Yep. Yep. What else? This is really good. We got a really good list here. We're going to compile this list. It's a lot.
We're
It is.
missing one.
So we're not even done
I
yet.
know we're missing.
We're
I
not.
don't even know. We're not even
Looking
done
for
yet.
one thing.
What happens if you're working on a belt-driven system?
Oh, okay, so we're doing commercials too.
We're just going to go through. Yeah, let's go.
Woo! Yeah, okay.
What happens if we're not? Oh yeah. Oh hey. Oh.
Yeah.
The
Oh,
belt.
They can
hey.
throw a belt, lose a belt, wrong
Cut
size
the belt. Forgot to install the
belt.
Right, the belt could
Forgot
be
to put a
slipping.
belt in.
The belt could be slipping. You could have a shiv that's adjusted. Somebody went and messed with the shiv, so now it's not producing nearly enough airflow. Why did you just do that?
Your belt
It
could
could
be.
be-
Sounds violent. I wasn't.
Adjust the shiv. Yeah.
Yeah.
Your belt.
That's
could
after
break.
you stab somebody, and then you're like, you know what? I didn't get it right the first time. Let me do that again. That's adjusting a shiv.
VFD could be
I come here
programmed
just for the
inaccurately.
You could have a VFD
Or
that's
on
poorly
camera.
programmed. Yep, and that would be in commercial. We'd call it that. All right, I'm gonna wait for these two knuckleheads to stop yucking it up over here.
Don't say
I mean,
funny things.
what, what do you think this is? Laurel and Hardy up in here? Wow.
That's right.
We're just chilling.
So there's a residential version. So hold on, Corey, because he's a commercial tech, talks about setting up a VFD, programming a VFD, which a VFD is a variable frequency drive to spin motors different speeds, right? So you're not stuck on 60 hertz, 60 cycles per second. But in residential, we have a version of that that's pretty much exactly the same thing. What is that called? What is the residential version of a variable frequency drive?
Solid state drive?
The inverter?
Solid state.
Or
drive.
solid. Yeah.
solid state.
I mean, solid state means electronic. That's all that means.
Well, you can use them for like a PSC motor. And
Okay,
ramp it
okay.
down enough.
All right. All right. Speaking specifically of blower motors, when we say ECM, electronically commutated motor, we're basically saying a VFD driven motor. And there is a VFD. The motor module on a ECM motor is a variable frequency drive. That's what it is. Right? You're taking single phase, in the case of residential ECM, you're taking single phase power, you're turning it into DC, and then you're taking that DC and you're switching it in order to spin the motor at a particular speed. Now, a lot of people will say, well, no, it's not actually an alternating current motor, though. It's a DC motor. Some people say it's a three-phase motor. But really, what makes it different is that rather than having this true sine wave that we get from the power company, you're actually just energizing, de-energizing at three different poles.
Pulse
Not three
width
different poles, but three
modulation.
different phases. What's that?
Pulse width modulation.
Pulse width modulation. That's a word you don't hear every day, ain't it? good old PWM. We're not going to go into that right now, all right? But it's a huge one, though. And it's one that we talked a little bit about last week, and I want to talk about it again because it's one that I know that we miss. Because you go in, we're going to go through a scenario here, okay? You go up to a system. I'm actually going to throw out some numbers here for the senior techs just so that we, are all on the same page. Go up to a system. It's a 410A system. You've got 90 suction on it. You've got 8 degrees of superheat outside. You've got a delta T of 25 degrees, 26 degrees, something like that. You've got a head pressure that's slightly low based on the outdoor temperature. I'm not going to try to come up with one right now, but it's slightly low. What is the root problem that caused those symptoms? It's airflow, right? TXV metering device. Sorry, I didn't tell you what metering device it was. Because your superheat is normal to low, your suction pressure is definitely low, your delta T is definitely low, and your head pressure is a little low. Right? Those are all indications of poor indoor airflow. So those are your symptoms. Then what do?
Replace the TXV several times.
You replace the TXV over and over and over again, and then say it's probably the compressor, and then say, I'm sorry, ma'am, this unit just ain't got no more life left in her.
Yep. I was replacing a TXV once, and I dropped the screw in the return, and it went.
Yeah, screw out never to go bloop when it falls into the return. Right. Hey.
The TXV put all this water in the return.
Again?
Yeah, that's it. Yeah, when a screw goes bloop, something to look for. So you go through all of that. Now you've diagnosed that it's an airflow problem. Most techs are going to go through the list of things we've already talked about, right? They're going to check the filter. They're going to look in the return. They're going to look at the blower wheel. They're going to look at the evaporator coil. They're going to do all that. And when they get done, a lot of technicians are going to call their manager or supervisor and say, I don't know what's going on with this system because I checked the airflow and it's fine. Right? Did you check the airflow?
If you
No.
didn't, it wasn't fine.
Right. You did because you connected tools to the system that gave you every indication that airflow was not fine. Right? They're telling you that it's not fine. But what do? You go through your list, and then at the end you say it's fine. But did you measure airflow? No. Let's say you were really good and you measured static pressure. And let's say your static pressure, you were running 0.5 total external static. It says right on the panel that that's what it's supposed to have. So my airflow is fine. But is measuring static pressure measuring airflow?
Nope.
No, it's just measuring pressure. Right? So if this blower isn't producing what it's supposed to be producing, if it's not moving the amount of air it's supposed to move, static pressure is meaningless. Doesn't mean anything, right? So if, for example, somebody landed the yellow wire on the wrong terminal on a single phase unit, they landed it on Y1 instead of Y/Y2, that's a carrier designation, but they landed it on the wrong terminal, that system's going to run low airflow. Let's say that they pulled the DH to R jumper and they didn't wire it up properly to the thermostat. If you don't have 24-volt call on that DH, what's it going to do? It's going to produce less airflow. And it's going to give us all these symptoms. Everything's going to look pristine. Everything's going to seem like it's working fine. Static pressure is fine. Everything's clean. What's the problem, right? But it's that the blower's motor isn't producing enough airflow because it is programmed in such a way that its inputs are telling it to produce less. What happens if it's a 4-ton unit and somebody went and set the pin to 3-ton? It's going to produce less airflow than it should have, right? What happens if it's a heat pump unit and the green wire is broken somewhere, the G call, so that way that blower never gets a G call in cool mode? What's going to happen to airflow? On a lot of systems, it's going to drop a lot because that's a programming feature. If you have a cool call without a G call on a lot of systems, not all, but on a lot of systems, it's going to produce lower airflow. So, and again, I beat these drums a lot. I cover this a lot, but there's a lot of things you've got to check. And even then, even after you do all that, once you confirm that, even once you look at the pin settings, even once you test to make sure you have a 24-volt call on G and Y/Y2, did you check airflow? The answer is no. So I'm not saying that you did anything wrong because you didn't, but don't say you checked airflow because you didn't. What would you have to do to check airflow?
You have to have a flow grid.
You'd have to have some sort of a tool that measures flow, and there are a few. True Flow Grid is a really good one. What are some others?
Anemometer.
You could use an anemometer. You could use a rotating vane anemometer, but that's only going to go Your typical large vane anemometer is only going to go at the vents, so you'd have to go to every vent in the whole house, do a traverse on each one, which means you have to move it slowly across it, then time average it, and then multiply it by all of them. But even then, if you have duct leakage, that number's not going to be right.
You put that little cookie tray thing in the filter that you were talking about.
Yes, that's the true flow grid. Yeah,
True flow.
of course. That's probably the best way, the most consistent way. You could do it with a large flow hood on the return. You could do it with a hot wire anemometer in the duct and do a traverse, do a log Chebyshev traverse and lay it all out with your different holes and measure it and take the time average and then calculate your velocity and then multiply that times the internal dimension of the duct, right? You could do that. Are you ever going to do that?
Nope.
Nope. Not, I mean, in commercial you might if you're a test and balance technician, but you're not going to do it. We're not going to do it. You're not going to do it,
I did it.
right?
I've done it.
You have.
And in this scenario, you don't need to.
And I'm not saying when I say you're not going to do it, I'm not saying it's, if those of you are like, well, you should do it. If you do it and you are good at it, then great, more power to you. But your average service technician is not going to do that, right? So the point is that being good at going through all the likely causes of low system airflow, being good at that is the whole game, right? But you have to go beyond the obvious. You have to go to the next step and the next step and the next step and look at the way that the blower is programmed. And then at the end, if you still really, the readings are telling you your airflow is low, but the system, everything you can look at, you're not finding anything, then now's the time to get an advanced tool like the True Flow Grid and just see for a fact how much airflow is moving through that unit. Because there's lots of weird things that can happen. Somebody could have put the wrong blower wheel in. Stuff like that that's can be hard to spot sometimes. There's some strange things that can happen. Yeah, what happens if the motor's running backwards? That's one that a lot of people fail to catch. Actually, probably the weirdest diagnosis I've ever had, and I'm only going to tell this story because it was weird that popped in my head, so it's probably not going to be useful to anyone, and I'm sorry. But I had a ECM motor that was running backwards, and it had been running the right way for a long time. This was not a brand new unit. It was like 3 or 4 years old, and it was just running backwards. So I, you know how to change the direction on a 3-phase motor? You just switch any 2 legs, right? So I thought, oh, well, a ECM motor is a 3-phase motor. So I pulled the end bell off, the motor module. I took the 3 wires and I just switched the pins. I pulled them out and just swapped them, and then it ran the right direction. I didn't think that would work, but it did, and that was weird.
I can do
So
that.
That's cool.
anyway, I'm not suggesting that you actually. I'm sure I did. Yeah, I've always been very good at tending to profit first, making sure that we quote for everything. Okay, so system airflow. In terms of the average technician, you're going to know that there's a problem with system airflow first by careful analysis of your system readings. And that's the point of today's class more than anything else, is to be able to spot an airflow problem and to know an airflow problem separate from other types of problems, so that when you see the measurements, as long as your tools are working properly, and I want to talk about that for a second before we even get into it, as long as your tools are working properly and you see certain indications, you know it's an airflow problem. You don't need to look at other weird things. Okay, you don't need to replace the TXV. You don't need to think, well, maybe it's the compressor, like that kind of stuff. You can know if it's an airflow problem or not based on the system readings. And that's what we're going to cover. Now, before we do that, a couple ground rules. Whenever you're using instruments, especially digital instruments, well, actually any instruments, but you need to make sure that at minimum they're zeroed, and then also watch them against one another. And I just wanted to point out something. If you look here at Measure Quick, which we've got, a live stream from the system here, you see that we've got a slight difference between the high side and the low side, which is just going to be a calibration difference between them. But it's in the acceptable range, right? We're under 1 psi. Now, what is the acceptable range? It depends on what you're doing. But for these purposes, within 1 psi is just fine. Right, not going to make a significant difference. Look here, our return dry bulb and our supply dry bulb are pretty different, right? Our return dry bulb, they're almost 3 degrees different. Now, hypothesize why that might be before we jump to the conclusion that there's a problem.
You're at a height
What was the question?
The supply dry bulb is 79.7. The return dry bulb is 76.9.
There's
You have-
cooler and denser.
You don't have them mapped right?
Hmm?
Are they mapped right?
They're mapped right.
They're right there.
They're right here. The reason is because
I don't know.
one is lower and one is higher. So there
yeah.
can be some stratification there. Now, is it that much? I don't know, but we would know if we turn the fan on, right? So if we run with the fan in the on position, then we would have a better sense. Now, be careful because the motor does add a little heat to it as well. So it's not perfect, but the best way would be to take them both and put them both right in the same airstream. If you're in doubt, put them right in the same airstream, run some air over them and see. Even just having them with still air like this, they're not going to be as accurate. These sensors are designed to have air moving over them. So putting them both in the return right next to each other and just checking is going to be a good practice, and we're going to do that. But the thing I'm wanting to show you here is it's worth paying attention to, right? If you just rush right in and start taking measurements, and you're not paying attention to if your tools have been zeroed and if they're measuring the same to each other, then you can make some pretty significant mistakes. 5 degrees of superheat 1 degree or one way or another can be enough to make you think that you do or don't have an airflow problem. And that's easy to get. Easy to get 5 degrees of superheat difference, right? So you got to know your tools and just pay attention to obvious things like that. The system's off, so they should be measuring the same, right? Okay, why aren't they? Hypothesize. Put them together, run it, let's see what we get. Right? Make sense? So always double check your tools. Before we get running on the system, I do want to talk through quickly about our primary indicators of low airflow. What is our number one primary refrigerant side indicator of low airflow, regardless of system type or metering device?
Low superheat.
Low
low suction line temperature.
Low suction line temperature is actually a great indicator. I actually prefer that over superheat even, because a TXV is going to hold your superheat where it's supposed to be, right? That TXV is going to start throttling. But your suction line temperature is still going to be low. Why?
Because you're setting liquid refrigerant.
Because what?
Because you have liquid refrigerant going
You're not
through
absorbing as much heat.
Because you're not picking up
Yeah.
as much heat, right? If you don't have enough air, you're not picking up as much heat. And so that drives down the evaporating temperature. So your evaporator coil gets colder. So let's say that you have a 40 degree evaporator coil with 10 degrees of superheat. What's your suction line temperature?
55.
40 degree evaporator coil,
Yeah,
10
yeah.
degrees of superheat is 40 plus 10 equals 50, right? So 40 degree evaporator, 40 degree suction saturation temperature plus 10 degrees of superheat equals 50 degree
I didn't have
suction
my
line.
calculator.
Right?
was
Right.
homeschooled.
I know, it's tough math. It's tough math. It's fuzzy math, as George W. Bush would say. That was my George W. Bush voice. It wasn't great. We're just gonna pretend like that didn't happen. Whew, wow. Yeah, too late. But now let's say that you have low airflow. And so when you have low airflow, you're going to have a lower evaporator temperature. So now let's say our evaporator temperature is 35 and we have 10 degrees of superheat. Now what's our suction line temperature going to be?
45.
45. Got it? To the extent that, this is kind of a neat thing. If you measure a suction line temperature, now we're talking residential air conditioning here, but if you measure a suction line temperature that's below 50 and the temperature inside the space is normal, and I'm talking about outside, temperature inside the space is normal, and you measure a suction line temperature below 50, very good likelihood you have low airflow, right? So an experienced technician will go up to a system, grab a suction line, and feel that it is especially cold, and you're looking for airflow. It really is kind of that simple. Now, I'm not telling you that that's how you do it. You don't just walk up and grab a suction line. But if a suction line is especially cold, probably airflow or low load in this case being in an air conditioning system, that would be a house that's too cold, right? Somebody set the thermostat way down and let it run. But under normal operating conditions, having a suction line below 50 degrees, more often than not, is going to be an indication of low airflow. Because if you had low refrigerant charge, what would your suction temperature be? High. If you had a restriction, what would your suction temperature be?
High.
High. If you had a bad TXV, what would your suction temperature be? High. Right? All those cases, it's going to be high. So if it's low, and the system's not operating properly, you have low suction pressure, you have low head pressure, pay attention to airflow first. Now, we're talking about airflow on the evaporator coil, but let's talk quickly about the condenser too. So in the evaporator coil, what does airflow do for the coil?
It boils off the refrigerant
Boils the refrigerant. Very good. So how does it do it?
by air over coil.
Heat transfer, right? So let's really break this down, okay? So air is what? What is air made of?
Molecules.
Air is made of, right, it's molecules, it's stuff, little tiny stuff, right? Air has weight and it takes up space. It's stuff, right? So as air moves over that evaporator coil, it comes in contact with the fins, the aluminum fins, right? That's what it comes in contact with first. And as it does that, it creates some turbulence, so it kind of starts bouncing around, and it imparts some of its heat to those aluminum fins. Why? Why does heat go from the air into the aluminum fins?
Aluminum fins are colder temperature.
They're at a lower temperature than the air, right? And so what direction does heat move?
From hot to cold.
Hot to cold, right? Let's just do a quick thought experiment. What would happen if that evaporator coil had no fins? What would happen if we took all the fins off of it?
It would still work sometimes.
What would happen?
The heat transfer is
Less
better.
heat transfer.
You'd have much less heat transfer, right? Why would you have much less heat transfer? You have less surface area, you have less turbulence. So there's less time and turbulence. There's less dwell time. Those molecules have less contact time, right? So they just rush right past. They're not sitting there and contacting those fins, which then contact the tubing, right? So what's going to happen to the pressure inside that evaporator coil with no fins?
It's gonna drop.
It's going to drop. Why again?
Pressure, temperature.
No heat transfer.
Because it's not having enough heat transferred in, right? It's the heat that's being absorbed into it that holds up that pressure. If you're not absorbing heat, that pressure is going to just keep diving and diving, right? Decrease in temperature equals decrease in pressure, right? We add heat to it, that holds the temperature up, that holds the pressure up. And we create this equilibrium. Remind me again, 75 degrees inside temperature, residential, typical unit. What's your coil temperature going to be?
40.
About 40 degrees, right? So if you have low airflow, what's going to happen to the coil temperature?
It's going to drop.
It's going to drop. What's going to happen to the pressure in the coil?
Drop.
What's going to happen to your suction pressure?
Drop.
What's going to happen to your head pressure?
Drop.
It's not a trick question. Head pressure drops too, right? What's going to happen to your compressor when you have low airflow? It's going to drop.
Fly away.
Yeah. Yeah. What's going to happen to your compressor?
Amp draws.
Amp draws what?
Drop.
The amp draws do drop. Why does the amp draw drop when you have low airflow?
Doing less work.
It's doing less work, right? Oh, okay. Go ahead. Mass, Simpson mass.
Whoa.
I like mass. I like a good conversation about mass. What's going on to mass when you have lower airflow?
The volume stays the same, the mass decreases.
Okay, the volume of what stays the same?
Refrigerant,
The volume of refrigerant where?
compressor.
Entering the compressor, being cycled through the system stays the same, but the mass is decreased. Why?
Lower load, lower heat content.
Because there's lower pressure, right? There's lower pressure means in a contained system, lower pressure means less mass if the substance is the same. So it's lighter. Easy way to think of it is low suction pressure means lighter gas. There's lighter gas coming back to that compressor. So on the good news, the compressor doesn't have to do as much work, right? So the amperage drops. But on the bad news, what else happens to the compressor?
It's not getting cooled off as much as it should be.
Okay, Alex said it gets flooded, and Eric says it doesn't get cooled off as much as it should be. Which one of those is true?
I'm going with Eric.
They can't be both true.
The answer is could be both of them, right? Could be,
No.
could be,
Yeah.
No.
could be.
Depends on the
If it's
conditions.
flooded, it's staying cool.
I'm not saying they're both happening at the same time.
Okay.
I'm saying
All right.
that
All right.
if you actually have liquid making it back to the compressor, that's a flooded condition, running flooded. But in that case, your mass is not lower. Your mass is much higher,
Yep.
to the extent that the compressor can't even compress it if it were to get into the compression chamber and it would explode the compressor head, right? So there's this fine line between light gas coming back and wet gas coming back that causes damage. But we're assuming here that we have some superheat, and so it is dry gas. It's light gas, and that's actually going to cause the compressor to overheat, even if the temperature of it is low. This is a tricky business because guys will say, "Well, look, my return gas temperature is 45 degrees. You told me that it's the refrigerant that cools the compressor, and you also told me that low airflow causes lower suction gas temperature. So why doesn't this lower temperature gas cool the compressor better? Wouldn't it cool it better? It's colder." The answer is no, it doesn't, because there's less of it, because it's light. It's light in the loafers. Are you still allowed to say that?
Yeah.
Okay. Bird says it's fine.
I've never heard
Eric
that.
says I'm not allowed to say that anymore.
We're
It's
children.
because you're wearing Crocs. That's why. Yeah. You feel personally attacked by that, don't
I'm
you?
personally attacked by this.
Yes.
Yeah.
Yes,
Those are
indeed.
loafers indeed.
All right, so there is this fine line. Can you overload a compressor by having the suction gas be too heavy?
No.
Just on the other side. Can you overload it?
No, sure.
Can a compressor actually do so much work
Yeah.
because the suction pressure is so high that it overloads?
Heck
Yes.
The answer is yes. And where do you see that in grocery refrigeration? When can that happen?
Freezers. You see a
Yeah.
lot of
Yeah.
pressure limiting TXVs in freezers to not
Yep.
overload compressors.
Yeah,
on
but when do
small
they
systems.
typically overload? There's two conditions where they are going to tend to overload without the pressure limiting TXVs or without the CPRs.
Put it on after defrost.
After defrost and hot pull down.
Yeah.
So when they're under massive load, and that would be after defrost and in hot pull down.
Rack down.
When that suction pressure is so high that that gas is so dense, it's so heavy, that that compressor has to do a lot of work to pump it. So compressors are dainty little pups. I mean, they need everything to be just right. You know, it's like Alex's mother. You know what I'm saying? Oh, I can't do anything right. That's a good one. All right. You're going to kick my butt. I got a little off on a side tangent there because the topic is airflow and the effects. So here's what we're going to do. We're going to go through, we're going to profile the equipment as we start it up. We're going to get it running and look at where it stands with it running normally. We're going to make sure our instruments are calibrated properly. And then we're going to create some airflow problems. We're going to first block off the supply, see what happens, reduce it slowly, see what happens to the system. Then we're going to throw some cardboard and place the filter, clog that up, and see what happens to all of our system measurements as we go.
Good old shopping bag. You find those in the filter occasionally.
Yeah, shopping bag and the filter, that'll do it too. Or the customer who doesn't take the plastic off the filter when they put it in.
Or uses a 3M filtrate, which is basically the same thing.
Basically the same thing, exactly, yeah.
Well, you're supposed to be a filter.
I'm sorry, 3M.
No.
Don't sue me.
It's a
First
very-
thing let's do is power the unit up and let's turn the blower on and put both of the probes in the same location and just make sure that they even out.
I don't even know.
We want to make sure that they're not too far off from one another. All right, there we go. So we're gonna get the breakers on. All right. Now it's running in cool mode. I guess that's fine. Might actually get slightly different.
Yeah, I put them in the return. Both of them?
Both of them. All right, so what we're watching for, actually, hold on. I'm going to show you how to do something cool on this. You can show touch indicators. So, see that?
Wow.
So, we're looking to make sure that our dry bulb and our wet bulbs stay pretty close together. And as you can see, they were quite a bit different initially. They're actually doing pretty good now. But we're also, one of them looks like it might have gone off. No, I guess not. What does that red dot mean? Does anybody know?
What happened?
They all have a red dot.
Okay, so the point is that we're looking good here. So now warm one up in your hands so that we can make sure that we put the right one in the right spot.
That's the
Okay,
supply.
so this is the supply, great. So put that one back up in the supply now. All right, try to get the probe a little closer to the vent. There we go, that'll work. All right, so now we need to profile the system and actually tell it what type of unit we have here. Just to,
I don't think we can use that word anymore either.
we can't ask about what kind of unit we have. That makes sense, So in order to profile outdoor temperature, because the outdoor temperature is actually the same as the return temperature, we're gonna go ahead and just put that in there. So our return temperature is 76 degrees. So we'll go and we'll make our return outdoor air temperature 76. Now I already set the airflow to 700 SCFM, which is something you can do. The Measure Quick it doesn't allow you to set in the profile for airflow anymore. So if you go back, yeah, the like standard airflow. So if you go back to the whole like CFM per ton where you can pick which one, it doesn't let you pick it. Like if you click the other ones, it doesn't do anything.
That's behind a paywall now.
Well, I don't know if that's why or not, but Jim was telling me something about it, but then he talked for 2 hours straight and I stopped listening. So we do need to set the metering device type. It is a TXV. The SEER rating, 13 to 16 SEER, that's what we've got. And then our refrigerant is our 410A. So all that looks good. Outdoor measurements, we already did that. The only thing we don't have is discharge line temperature. If we had a different line clamp, another one, we could put that on the discharge line inside near the compressor. Indoor measurements, we're pulling all of these in from the probe. So when you see ones that have a calculator, that means that's a calculated measurement. So it's taking the relative humidity and the return temperature together and it's calculating the wet bulb. Same thing on the supply. Now I entered a measured CFM of 700, but that's just because it's a 2-ton unit. I was just kind of bypassing the internal thing, but as you can see, they've got an estimated CFM of 340, and the reason why it's doing that is because the tonnage, I always hit the wrong one. System ID and system info seem so similar. The tonnage is set at 12,000, so it should be set at 2 tons. Target subcooling, it says 10. Let's see if that's correct on the data plate. It's taking me a really long time to find this. It's 11. Whew, big difference. All right, so now we're pretty much profiled. We're missing a couple probes here, but we're pretty much profiled the way we're supposed to be. So you can see 329 CFM per ton, pretty close. In Florida, 350 CFM per ton, is pretty much what we're looking for. So everything's looking pretty good. Now, you're gonna notice that our target here is actually a little bit high. And that's because we have a high efficiency coil, and I think he also removed that. That used to exist here. But anyway, let's just look at what we've got now. So you can see both of these are really close to being within the green zone. The only thing here is that our evaporator temperature is a little bit high, but that's actually pretty normal based on the way that Measure Quick works and our high latent high moisture conditions. So our suction pressure of anything is a little high. Let's go through our, we got our temperature split right dead in the middle of what would be expected here, our delta T. And then our system capacity. Really good system capacity. It's a 2-ton unit and we're producing right at 24,000 BTUs. We've got crazy low sensible heat ratio, which when your sensible heat ratio is low, your latent heat ratio is high, right? So that means how much of the heat being removed is temperature change and how much of the heat being removed is water, turning it into condensation. So probably do need to make sure this thing's actually plugged in. All right, looks all right. Before it was dumping water all over the place. We're moving a lot of moisture. If we wanted to see how much moisture that we're moving, 9.2 pounds per hour is how much water I think sucking out of the air. It's a lot of water. Do you know how much volume a pound of water is?
Yes.
How much?
1 pound.
Volume. A pound is mass.
Volume, evaporated water, or you talking about?
8 pounds per gallon.
I don't know.
It's a pint. So a pint is a pound the world around. Come on, everybody knows that. We had a trainer come in here one time and he said that like 50,000 times. You remember him saying that?
No.
A pint's a pound the world around. Remember that? It's not ringing any bells. That's just how he said it too. Let me do it again. A pint's a pound the world around. See, now you won't forget it either. All right, now why don't we have any of this data? Why isn't any of this showing up? EER, SEER, CESP, and fan efficacy.
We didn't add in enough
We don't have,
measurements.
we're taking electrical.
Right, we're not taking electrical measurements, so we don't have a redfish meter hooked up actually taking real-time wattage. That's the only way it's going to output that. Either if I manually enter it or if I'm taking that real-time wattage. Why don't I have total external static pressure?
Because you don't have
Because I don't have my static pressure probes hooked up, right? But I would have it if I had those hooked up. Then you've got your outdoor air temperature. Of course, we're not actually outdoors, but this is what it is outside. This is pulled through an online service. Atmospheric pressure, relative humidity outdoors. Let's focus here. Our suction line temperature is
too low.
just above 50 degrees. Yeah,
Have
so
a
we can
problem
see
click on it. Full information about that problem.
our superheat is hunting a little bit. What's the first thing that you would do if you ran into this system and these are the measurements that you were getting in real life? What's the first thing you would do?
I've let the system run for quite a while.
Let it run a while first, yeah. Then what would you do if it kept doing it?
Ask them why they
I
call
would
it.
check if the THC bulb was insulated.
Sensing bulb, yep. You check to see if the sensing bulb was insulated and making proper contact, or if somebody used zip ties to put it on the suction line.
Especially if it's a
Works
ream.
just fine.
No, it doesn't.
It does.
No, it doesn't.
Yes, it does.
No,
You
it
gotta
doesn't.
insulate it first, and then you gotta pop it.
It works just fine for a few days.
Yeah, until it goes sideways. Yeah,
Yeah.
exactly. Exactly. You got it. So the bulb has to be making good contact, use a conductive strap, and then insulate it.
And make sure it's not in the right location. Ream equipment.
Oh,
Just saying.
It really doesn't matter.
oh,
You can put it anywhere you want.
it's going down now.
I put it outside.
No, what Eric, explain what you're saying.
So on
Speak to Corey because he's
on
going to get
certain-
into this argument again. Go
on
ahead.
certain
Eric.
equipment, people will mount it onto a place on the suction header on the evaporator where it's not sensing after all of the return bends have entered the suction header, especially on ream equipment, because people are like, oh, let's just put it at the top right here where it's only sensing a third of the coil's return on the suction header.
So Eric's not saying that on a 3/4 inch suction line that putting it on the top or the side of the bottom is going to make a huge difference.
Obviously, you got to drill a hole through the suction line and not the bulb.
Into it, right. This is not the same temperature as the refrigerant on the inside, all right? So, what do we call what this system is doing right now? What do we call this? There's a term for this. It's hunting, that's the moving around. But low superheat is called what?
Flooding.
Flooding, overfeeding is the
Overfeeding.
term I would use. It's not actually flooding because we don't have zero superheat.
True.
Zero superheat would be flooding.
Point one.
But
Do a pull down.
we're overfeeding our evaporator coil. In fact,
Are we done?
superheat is an indication of how well you're feeding your evaporator coil. High superheat means you're not feeding it fully. Low superheat means you're feeding it too much. Subcooling tells you how much liquid you're stacking in your condenser. High subcooling means you're stacking too much. Low subcooling means you're not stacking enough. I just came across this way of describing both of those and I really like it. How do you feel about it?
That's beautiful. Say it again.
No, I don't want to. I just said it.
I feel some kind of way.
I trademark.
Some kind of what?
It's yours.
I feel some kind of way.
Feel some kind of way. Okay, good. I just said something way worse than that. Well, that's good. All right. So anyway, I don't like how low the superheat is, but everything else is really in line. Suction line temperature is a little low, but that's because our superheat's low. Right? If we got our superheat up, then our suction line temperature. But you know what? Let's go ahead and do this because we got plenty of time here. Let's go ahead and see if we can figure out why this might be happening. So let's pull it. Let's shut it off. Let's pull it open. And let's see if maybe there is a bulb issue or something else going on. Bulb is actually factory strapped with a zip tie. I've never seen that before. Maybe is there another strap underneath that?
inside.
There's another one on the inside. Okay, all right. But this was open, so it's sucking air in, which could be affecting and causing it to overfeed. So we're going to seal that up and see if that fixes the problem. So notice my superheat and subcool.
Whoa.
What?
Wow.
We found the issue.
Your superheat and subcool should always be zero when the system is off. And that actually, it's a very interesting way of validating your tool's calibration. Because if they were measuring something other than that, that would show a miscalibration in between your potential. Miscalibration.
Okay.
Okay.
Whoa. Somebody needs a torque wrench.
We just need to make sure that we don't have any threads left on those screws when we're done.
It's super cold.
Our return static is next to nothing.
Put a piece of cardboard in there.
There's that other hole sitting right there that's exactly for that purpose.
Yeah, but it's not good enough.
Oh, okay.
It's too low, and it's sticking, like, not in the flow of the forward.
All right, so our return inner supply are very, very low. Total external static is 0.2.
Perfect.
X13 in that unit?
All right, so we want to watch this. Oh, we lost one of our probes there.
It'll come back on.
Yeah, we got the insulation's got to cool down.
Yeah.
The insulation was warm.
Shut does kind of slow down.
I know, that's why I said it.
Okay.
Was our subcooling this? Our subcooling wasn't this low
No,
before.
our
was it?
subcooling was
It was
70.
low when the unit first started up, though. It took a few minutes to come
Yeah.
up.
Somebody mischarged it because the TXV.
You ever heard anybody let the unit run?
Let the unit- You know what you got to do? You got to let it run a little bit, right? So you see our suction pressure is actually a little bit lower than it was before. A little bit. Of course, it hasn't run very long either.
Yeah.
Yeah. Oh, hey, there it comes. It's when the system is unstable, you can bypass that now. So you can clear the unstable. System is operating. Okay, so this is the new thing. This is why you can't set airflow now. This is probably what Jim was telling me when I got bored. System is operating with characteristics of a 13 to 17 SEER system with airflow optimized for warm, humid climates. So rather than saying it's a problem, it's just saying, look, based on the measurements that you're getting, this looks like what you've got, and sure enough, that's what we've got, so nothing to worry about, right? So you see here, it's still calling out TXV, it's still calling TXV bulb may be loose. You see that popping up every once in a while. We're really losing our tools here.
You just wait a
They
second, it
will all
will
go
come
off.
back on.
Every 2 hours.
The other one I didn't turn
The
on.
green light's still blinking, isn't
Just
it?
about to lose them.
Redo. I did 3 now, so.
Okay, there it is. I guess if I'm looking for subcooling, I should be looking at the liquid line, not the suction line, huh?
Yeah.
I should have attended class on this. All right, yeah, we're looking pretty good. Other than being unstable because we haven't let it run long enough, we're definitely doing better now. I mean, other than now, our subcooling's looking a little bit on the low side, but well, here's a question: is this going to make our system capacity better or worse based on what we just did?
Oh, it's gonna be definitely worse.
It's going to be worse.
What?
Because before we were running a near flooded evaporator coil. So now we're actually feeding less of the evaporator coil. Now it's not much. It's not going to make a significant difference. But you see,
23.7 instead of 24.
we are lower. But you don't want to overfeed your evaporator coil. If you get below your minimum stable superheat, you can lose control and actually dive to zero superheat, resulting in flooding. Flood back. Yeah, we're looking good. Subcool's coming up. Whoa. Our superheat just went really high. 114 degrees superheat? I didn't even know that was possible. We can see that we're in pretty good shape.
That's the worst.
So we're going to go ahead now and start making some airflow adjustments. And we're going to pay attention to what changes. All right, superheat's still a little low, but it's acceptable. Now, if we look up here, we got a red flag. It's not a black flag, but it is saying the sensible capacity is running a little low now. Yes, Corey?
What if we swap the probes to the outlet of the evaporator for the superheat?
Yes. So that's it. So Corey makes a good point. What would happen if we measured superheat at the evaporator outlet? Or what would happen? Would that measurement be higher or lower superheat?
You're gonna have well, on this particular system, probably not much different.
Right. Not much because you have almost no line
Yeah,
set.
but it will be lower.
Yeah, it'll be lower. So if you did this on a grocery store and you were measuring it out here, that would be almost meaningless as far as the case.
Yeah.
You have to measure it at the case. You have to measure it at the outlet of the evaporator coil. And in fact, for the most important thing is that the superheat is right at the outlet of the evaporator coil. But we do care what it is at the compressor as well, because if it's way too high, that can cause compressor overheating. Or if it's zero, that could cause.
That's what's good about probes, though, is that you can actually do that.
Yep. Yep. All right, so let's go ahead and start by cranking down our supply airflow. Let's move it and get our static pressure. We'll watch our static pressure.
Is that X13 in that unit, Brian?
Oh, okay, this is why we don't.
Okay.
There's a damper on the top too.
We're gonna keep that one open.
Yeah, the damper on top. Yeah, that's going to stay open. We're going to watch our static pressure. Yeah, that ladder's a little sketchy. I think it's like 90%. Yeah, almost close it. It's going to be hard to get this thing to shut down airflow because of how short the ducts are and everything. Make her nice and noisy. Yeah, and even then, like, our static pressure hardly changed because of where the probe is positioned. So what's going on? What do we notice changed?
Okay, so what's changed? You said our suction line temperature is dramatically falling. Yeah.
She's dropping hard, right?
In the danger zone.
Superheat's dropping. Now, superheat will throttle back once the valve adjusts. But you're going to notice our suction line temperature noticeably decreased with that change. Now the motor is compensating for this restriction too, so let's see what happened to our head pressure. So our head pressure, all right, so we were at 293. I think we're pretty much at the same place. Yeah, so we can still see here, the main thing that's changed is our suction line temperature drop. Let's go ahead and make this airflow problem worse. Let's jam the cardboard in the return now.
Stacking liquid in the condenser.
So that's what it means. So when you have higher subcooling, you're stacking more liquid. Why would you be stacking more liquid? Because your valve is closing. Your valve is closing to make sure it doesn't overfeed the evaporator coil. All right, now Bert is severely plugging the return. You're going to notice our air temperature split will probably start increasing as well as we move air more slowly over that evaporator coil. It's going to give up more heat. Our latent capacity is going sky high because we're moving less air.
What about the pressure ratio?
Look at our total capacity.
Our total is saying that it's going higher, but it's because I fixed the airflow at 700. So let's go in and delete that out. Ooh, look at our total external static now. Now we're over 1 inch of total external static. So now we've got a real airflow problem.
Loosen the belt.
And you can see our airflow is down at 500 is the estimated airflow.
Oh, you just tripped it.
Now we're short cycling the equipment.
No, we have a time delay.
We should probably glue that piece into place, you know? Unfortunately, now we have to wait longer again. Here's what we're showing. So superheat is being modulated by the expansion valve. You see it jumps around a little bit, but it still kind of stays in the same zone. As we reduce that airflow, the main thing that's happening is that suction line temperature is dropping. And we also noticed that our subcooling is also climbing because more of that refrigerant is ending up in the condenser, stacking up against that liquid line, up against the metering device in the liquid line. Our delta T is going to go really high because the air is moving more slowly over the evaporator coil. So the point just being that we clearly have an airflow problem. Right now, because we short cycled it, it's not stable enough for Electric to tell us that. But once it does stabilize, when we click this top indicator up here on the top right, it's definitely going to tell us airflow is the problem. Also because Measure Quick knows it's a problem because it's actually showing we're currently running 249 CFM per ton, which is way lower than we should. And of course, our static pressure is way up here in the red. If you want to learn more about static pressure, you can just go to this website. It's a really good website. All right, that's basically all I wanted to show you. Any questions about that? Anything to add? Anything? Why?
I want to get it to 2.
It won't go to 2.
Let's take a piece of flex and do some supplying.
There's usually the motor will limit itself.
The reason it's not is because this is a constant torque motor. And so it is ramping up in order to compensate for the poor airflow.
What if we take the evaporator panel off the door?
Oh, it's a good one. Yeah. Want to do that? No. Bert says no. Because because we're shooting video, we'd have to shut the power off before we pulled it off, and then.
Really? Oh,
Yeah.
yeah, safety.
No, you can pull the Y collar behind the stat in the magic box pulse. So the blower shuts off. The G collar.
YNG going to the blower.
Yeah, but you'd have to open up the
Yeah,
panel,
we'd have
that's the
to,
thing.
and we have to put a jumper in too and remove it.
And low voltage can still hurt you.
Of course, keep the condenser on.
Yep. You don't mess around with low voltage.
Anyway, I think we've sufficiently demonstrated. I think we've sufficiently demonstrated how to use Measure Quick. We've demonstrated that the primary indicator is suction temperature, and we also learned that superheat doesn't actually drop with the TXV. It might be on the low side, but it's not gonna drop because the TXV is holding it up, and our subcooling does increase a little bit. Yeah, so our suction temp is now
0.4. Woo! All you need is 0.1. Remember that.
That's what I want to see.
and now we're
0.0000000.
now we're really diving. Yeah, so now you can see we're getting at the bottom end of our target here, and we're definitely at the bottom end of our target here. So these together definitely indicate low airflow.
Interestingly enough, it's still not going to freeze if it's.
Yeah, I know, because we have enough load in here. The temperature dropped significantly.
Well, we have 76-degree return even with all that resistance. Actually, it's starting to drop more now.
Yeah, it'll get there.
You trying to ice it up?
Oh yeah, let's ice it up.
Make ice.
Yeah, we're
Oh yeah.
definitely diving now.
No, one time I.
But even then, like you've got to get, just getting your evaporator coil to 32 degrees, it's not going to freeze like that. It's got to get below 32 degrees, a ways below, before it's actually going to start freezing.
You know,
It takes runtime. Which is why you'll have units that don't freeze during the edge seasons, and then when the summer comes along, they'll start freezing just because they get that longer runtime, long enough for them to stay frozen. All right, that's enough. Thank you all. Great class. Appreciate you.
Appreciate you.
Yeehaw.
Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come out. HVAC School is far more than a YouTube channel. You can find out more by going to hvacrschool.com, which is our website and hub for all of our content, including tech tips, videos, podcasts, and so much more. You can also subscribe to the podcast on any podcast app of your choosing. You can also join our Facebook group if you want to weigh in on the conversation yourself. Thanks again for watching.